So yesterday we talked about chi-square tests, and all we did was name the tests, right? We went over homogeneity and independence. So homogeneity, you have two different groups that were sampled independently. For independence, you have one group that was sampled. Again, you guys did the homework where you just named the test, and a lot of you guys got caught up in looking at the tables. You can't look at the tables because the tables don't tell you anything. The tables don't tell you how the data was collected, and that's what makes the difference, is how the data was collected. All right? So I could do two individual samples and put stuff into a table. I could also do one sample and put stuff into the same table. All right? So it all depends on where the information comes from. So make sure you keep that in mind. Today we're actually going to do the test. So still a four-step process for a hypothesis test. The first thing you do is write the hypotheses. Again, for homogeneity, you're looking to see if the distribution within or between the two groups is the same or not. All right, so the null is the distribution is the same. The alternative is that it's not. For independence, you're looking to see if the two variables are independent or not. Okay, so make sure you keep that in mind. After we do the hypotheses, we check our conditions. So we have to, again, make sure we have counts. You do not have to write that out. You don't need to say we have counted data, but that's something you have to know in your mind, that we have to have counts in our tables. We can't have proportions in our tables. We need the actual number of people in our tables. Right? Yes? Yes. All right, independence. Now, if you have a test for independence, then that means you only have one sample. So you're assuming all the individuals in the sample are independent of each other. Right? Remember, you're testing if the variables are independent, not if the people are. So your conditions, you check the individuals. Are the individuals independent? If you're talking about a test for homogeneity, you have two samples. So you want all the individuals within each sample to be independent, but you also want the two samples to be independent of each other. I'm glad I spelled groups with two S's there. That's awesome. Okay, so you need to check this if you're doing homogeneity. Okay? Because you have two different samples. Does that make sense? Randomization, if you can check it. Sometimes when you do test for homogeneity, it doesn't necessarily make sense that you would be doing that if you're doing some sort of experiment or something. But if you can check it, go ahead and do so. Did you randomly sample the group, or did you randomly sample two groups? Sometimes they're just taking a census. Like one of the problems yesterday was the New York Police Department. They just took the entire department. It was one sample. They took the entire department and they just classified everybody as something. So it wasn't really random, and it's not really a good representation. It is, that's what it is, right? It's the entire police department. So you wouldn't necessarily need to check randomization there because you have everybody. And then you have expected cell frequency. Now, just like in goodness of fit, you have to have expected counts of greater than 5 for all of the categories. Okay? But here's the problem. You have a two-way table now. And so the expected counts are a little wishy-washy. You can't just like go through. They're not giving you a percentage that you can go back and find the expected count. So this is how you find them. And this is what's going to happen on the AP multiple choice quite often. They're going to say, here's this table, and we did a chi-square test for whatever. And they're going to say, how many people do you expect to fit into this category? And then they're going to write the answer in this format. They're not going to figure out the actual number. They're just going to write it just like this. So to find the expected cell frequency, you take the row total times the column total and divide by the table total. And they're going to write it out just like that. So they'll do like 20 times 45 over blah, blah, blah. Like that's what they're going to do. Right? And they won't even figure out the actual number. They just set it up like just this. So I want you to see that and know that. Now, when we actually do the mechanics, we're going to let the calculator do all the expected cell frequencies for us. But if you're just doing a multiple choice question, then you should just know what that looks like so you can do it really quickly. So I can type everything in and look for it. Okay? Questions about the conditions? Again, then you would write a sentence and make sure you're naming your test, chi-square test of independence, chi-square test of homogeneity. And then we're going to do the mechanics. So the mechanics are very similar to that of a goodness of fit test. You still have the same statistic. Observed minus expected squared over expected, and you add them all together. Again, that takes longer if you're doing a two-way table because you don't necessarily have just a list 1 and a list 2. You have a table of information and then a table of information for expected counts. So it's not necessarily easy to just do that by hand. In fact, I would encourage you not to do that by hand, and we're going to do it in the calculator. I just don't think anyone has sufficient time to do that on the AP exam. Degrees of freedom, because you have to have degrees of freedom. The calculator will tell you, but you also need to know how you find them, because again, on the AP multiple choice, it might just give you a scenario and tell you how many categories there are for each variable, and then you have to figure out the degrees of freedom without having any numbers ready to put into the calculator. So that would be tragic if you're depending on it to do it for you. With goodness of fit, we have the number of categories minus 1, right? Here's almost the same thing if you think about it as there's categories as rows and there's categories as columns. It's the categories minus 1 times the categories minus 1. Rows minus 1 times the columns minus 1. So you're sort of multiplying those two variables together if you think about it that way. Okay? And again, if you have your chi-square, you can use chi-square CDF to figure out your p-value. And again, for chi-square, the lower boundary is always, always, always your chi-square value. Okay? Question. We're going to do some examples, but general questions. And the last step is the conclusion. That's the same we've been doing forever. All right, then I've got 2 examples. We don't have to do all of them. We can look at both. So here's the first one. A random survey of autos parked in the student lot and the staff lot at a large university classify the brands by country of origin as seen in the table. Are there differences in the national origins of cars driven by students and staff? So the first thing you have to decide is question A, is this a test of independence or homogeneity? So think very carefully about this as independence or homogeneity. Do you have 1 sample or 2? 2. You have a random survey of cars in a student lot and a random survey of cars in a staff lot. So that's 2 samples, right? So you have a test for homogeneity. Yeah, you have 2 different lots. You can't sample all that together. It's a university, so it's huge. Yeah. We had the same thing at Murray State. It's all by colored tag. Okay. Homogeneity. On part B, it says write the appropriate hypotheses. So for homogeneity, we assume in our null hypothesis that the distribution is the same for the groups. So we need to look at what they're asking us about. And they're asking us specifically, are there differences in the national origins of cars? So we're talking about the distribution of car origin. Okay? So for our null hypothesis, the distribution of car origin is the same for students and staff. So then our alternative is the distribution is not the same, or it's different. Any questions about where those hypotheses came from? So we need to check some conditions. That's part C. Do we have counted data in our table? We have counts. Yes. You don't have to write that down. Just make sure before you move forward. So the next one you talk about is independence. We have 2 different samples. So we need to assume that the student lot and staff lot are independent of each other. And the cars within each lot are independent. Any questions about independence? Randomness, they tell you in the question that this was a random survey of cars. And so then we have our last things are expected cell frequencies. All right. So let me show you how to do this in the calculator. It does the mechanics too, so I'll show you in the calculator. But it'll show you your expected counts and your p-value and chi-square statistic and all that stuff too. Now, if you're going to do it by hand, like let's say the question didn't ask you the whole entire test, and because again, it could very well just be a multiple choice question, and it said, how many students do you expect to drive European cars? Right? So let's say just ask that. How many students do you expect to drive European cars? Again, that's an observed count, so it's not, the answer's not 33. You need to find all the totals. So I found them already. So 195, 164. So if I was going to find the expected count just for that section, I would take the row total, 45, times the column total, 195, and divide by the table total. Again, if it's a multiple choice question, it's probably going to be exactly in that format. They're not even going to multiply it all out for you. If you just multiply it all out, you get 24.4. All right, so make sure you know how to find a singular expected count. On the quiz, I'm going to ask for you to find me a singular expected count and show me the calculation. So you can't just find it in your calculator and then tell me the number. All right, so let's look at all the expected counts in the calculator to make sure they're all greater than 5. So here's what we do. We have a two-way table, so we can't just put this to a list anymore. We have to put it in matrices. So go to above the reciprocal button or underneath the math button. Scroll over to edit. Matrices are always given by rows by columns. So we have 3 rows and 2 columns. But at least here you can see that it's backwards because it'll be the wrong size. All right, then we just fill in their numbers. So 107, 105. It goes across ways first. 33, 12, 55. So that represents our data that we currently have. Right? All right. Now, again, you could do it all by hand, and you could do that calculation for expected count for every single one of these. But again, if you're on the AP exam, you don't have time for that. So we're going to do a chi-square test in our calculator. And so it's going to give us all the stuff. But in the background, it gives us all the observed numbers. And that's what we really want right now to check our conditions. So if you go to your test menu, so stat tests, and you need to scroll up, it's just easier. Just scroll up. There should be chi-square test. And it asks for an observed and expected. Your observed matrix needs to be whatever you just put those numbers into. So if you didn't put it into matrix A, then make sure you change it to whatever matrix you put the numbers into. Expected, you can fill in whatever matrix you want. So you can go to the matrix menu, and you can pick B, C, D, E, F, G, whatever, as long as it's not A, because you already have numbers in that. All right? Pick whatever matrix you want it to be, and it's going to write over it. Yes. No, you can't empty matrices in an easy way on here, so it just writes over it. So it's just telling you for the expected, it's telling you it's going to store it in this matrix. So observed, we had to put a matrix in. That's what we already have in the calculator. Expected, it's going to write over. So where do you want to store it? Does that make sense? All right. So then we're going to calculate. I'm going to write these numbers down for next time. So I've got my chi-square. We can go back and look at this later, but I'm trying to save myself some time. But what's really neat is, it doesn't say it, but your observed counts were in matrix A, and now all of the expected counts are calculated for you and put into matrix B. So you go to the matrix menu, and you just hit matrix B and hit enter, it filled in all of the expected counts. So I would expect 115.2 students to have American cars. It's in the exact same order as this table is. I would expect 96.8 staff members to have American cars. Is this making sense? Remember I said it was 24.4 earlier for students with European cars? It tells you 24.4. All right, so it gives you all of the expected counts. You don't have to come up with them on your own. Questions about that? Okay, so are all of those numbers greater than 5? Because that's what we're really looking at right now. They look like they're all greater than 5 to me. Right? So my last condition would be expected counts are all greater than 5. Okay? Again, after the conditions are met. So I can perform a chi-square test of homogeneity. Okay, any questions about the conditions? All right, so for the mechanics, let's just find the p-value. Again, it would just take a really long time for you to do all this by hand. Remember, chi-square means I would have to take a 107 minus that 115 number, square it, and divide by 115. And then I have to do 33 minus 24.4 and square it, and then divide by 24.4. I do that for all 6 numbers, and then add them all together, and that's how you get chi-square. No one has time for that, so I just did it in the calculator, right? So the calculator function goes through and it did it for you. So I'm going to go back and look at it again. So it did that for you. It calculated the expected counts for you, then it went back and subtracted them all, squared them, divided by the expected, and added them all together for you. Okay, so that's really easy. So that's too much to do in 10 minutes on a free response question. So my chi-square value is 7.83. My p-value then is 0.02. Awesome. And my degrees of freedom is 2. Again, you need to know how to calculate that in case it just asks you for the degrees of freedom and they don't give you a chart. So the degrees of freedom is rows minus 1 times columns minus 1. So 2 times 1 is 2. So make sure you know that. Any questions so far? So E, so state your conclusion and analysis. So what do we say about our p-value? It's low. So we reject the null, perfect. And what does that mean then? Right. It means there's evidence that the distribution of car origin is different between students and staff. Any questions about that? So these shouldn't take super long because I'm telling you to do a bunch of the math in your calculator. I'm giving you access to that because, again, no one has time for that. When you have 12 minutes per question on a free response, you don't have time to go through and calculate a statistic or accepted statistic for each one of those and then calculate all the differences square. You don't have time. With good as a fit, it's easier because it's just lists and you can do it in your calculator anyway. And the expected counts aren't hard to find. These it's too much time. Okay? Any questions about this example? All right, I want to quickly look at another one because we haven't really done the chi-square test of independence. I want to talk about what the hypotheses would look like. Then I also want to talk about how the table is set up because this is something that AP people would probably do at some point just to throw you off because they're mean. And that way we can practice again with your calculator. So here it says, medical researchers followed 6,272 Swedish men for 30 years to see if there's any association between the amount of fish in their diet and prostate cancer. Is this a survey, a retrospective study, a prospective study, or an experiment? It's not an experiment. Good. Why is it not an experiment? Right, there's no treatments being applied. It's not a survey. They didn't ask a bunch of questions. Prospective study, and why is it prospective, not retrospective? Right. They followed these people for 30 years. So they identified them and then followed them 30 years into the future. All right. Is this a test of homogeneity or independence? I gave you that answer a few seconds ago when I talked about this problem. But if you look at the setup, how many samples were there? Was there one or two samples then? One. They just followed this one group of people. So one group of people would indicate independence anyway. Right? Oh, I didn't hear you say what. I'm sorry. So C says, do you see evidence of an association between the amount of fish in a man's diet and his risk of developing prostate cancer? So we know it's a test of independence, so we have to write some hypotheses. Okay? So when you're writing hypotheses for independence, there's two ways to write them. And I need you to pick a way and stick with it, or you'll get confused. Because they seem opposite of each other, so we need to just pick one way and write them that way every time. So in a test of independence, your null hypothesis should be that the variables are independent. So we could say fish consumption and incidence of prostate cancer are independent. Now, you might see this written differently because it asks about an association. So if you say they are independent, you could also say are not associated. That's the other way of writing it. So you say they are independent or you say they're not associated. Don't get confused because then what's going to happen, you guys are going to write that they're not independent in the null because you remember not associated. So pick one way, independence or association, and stick with it. The alternative then is that fish consumption and prostate cancer are not independent. Again, that means they are associated. So pick either what I wrote in black or pick what I wrote in red and do it every single time so you don't confuse yourself. Okay? After we do the hypotheses, we got to check the conditions. I'm not going to write them out this time. Again, we know we have counts, but please look at the table because this is what sometimes AP people like to do. What is wrong with the table as it is right now? Right, you have one column that shows people with prostate cancer, but the other column just says the total people in that category. That's not what we're looking for. We need a table that has fish consumption, and then it has prostate cancer or not. I don't need that first column. That first column is going to make this a mess because you're going to just look at it and go, oh, here are the numbers, like I did first period because I wasn't paying attention. So make sure that you're looking at it. So not prostate cancer, and you have to figure out all these numbers. You have to subtract, right? So this would be 110. I did all these, so I'm going to write them down. And then you want to get rid of this and not look at it so you don't type the wrong things in. Right, so be careful that you actually know what you're looking at. You just don't assume that the table they give you is in the right format. So we have counts in our table, not a problem. We're talking about independence. Now, we have a test of independence, so we only have one group that's being sampled. So what do we need to check when we check the independence assumption? Right, so all of the men should be independent of each other. Right, there's only one group of people, so we just want to make sure that all 6,272 Swedish men are independent of each other. Okay? They're not influencing the fish consumption of the others. That's probably, Swedish should be bad since that's sugar. All right, so check independence. It's not a random sample, but we did a prospective study. So we're assuming this group of men is a good representation of men, or of Swedish men, if that. And then we need to check the expected counts. So again, how am I going to check the expected counts without having to do this for days? Use your matrix, use the test, and just look at the expected count. So we're going to type it in. This time we have a 4 by 2 matrix. We have 4 rows, 2 columns. So I have 14, 110, so on and so forth. Nope. The stat test, chi-square test. I put my observed in A. You can put the expected in B or wherever you want to put them. I'm going to write this down for later. If I go back to my matrix menu then, in matrix B, we can see all the expected counts. So I need to make sure all of these are greater than 5. So 9 is greater than 5. Obviously, the rest of them are greater than 5 on that column. Over here, definitely all of them are greater than 5. So our expected counts are all greater than 5. That's the other condition you check. And so then we say we have the conditions met, so we can do a chi-square test of independence. All right, we already did the test in the calculator, right? So I have my chi-square statistic. I have the p-value, have degrees of freedom. So what's my conclusion going to be? Conclusion. The p-value is high. It's very high. We failed to reject, which means you can just say that we can assume that the fish consumption and incidence of prostate cancer are independent. Right? Any questions about that? Again, be able to answer some of these questions. Be able to answer or do the calculation for, someone's going to tell me how to do it in a second. What's the expected number of men that would have consumed a large portion of fish in their diet and have prostate cancer? Right? That's going to be whatever that row total is times the column total divided by the table total. Right? You should be able to figure that out and write it out and show me. I was going to ask you to find the degrees of freedom for this. You should be able to figure that out without doing the calculator. We have 4 rows, minus 1, 2 columns, minus 1. 3 times 1 is 3, right? You want to do those little things because they're going to ask you those little things. Any questions? D, does this study prove that eating fish does not prevent prostate cancer? No. We see associations, but we do not ever see direct cause and effect. Right? Any other questions? What?
When I put it for the matrix figure, can I do a chi-square test for it, but I can't see the individual.
Could you? Do you have a similar matrix menu that I do? That's different. We'll look it up. Then I will look up the inspired directions in that book in a second. Other questions? All right, you were supposed to do the naming the test stuff yesterday, so if I haven't seen that, make sure I see that. Then here's your assignment.